Welcome to another video lecture. So today we'll discuss with the negative clamper. So in the previous lecture, I already discussed about the positive clamper. So now I'm going to discuss about the negative clamper. So in negative clamper, the input waveform is shifted towards the downwards or shifted towards the negative axis. So you can see in the diagram, we have an input voltage VI and we have a capacitor where the voltage drop across capacitor is equal to VC. We have a diode and a load resistor parallel to each other, and from the across the load resistor I am calculating the output voltage V0. So I am supplying a input voltage VI here. So VI equal to Vm sin omega t. So in Vm sin omega t, the maximum value of the voltage equal to Vm and the minimum value of the voltage equal to minus Vm. So before starting, as I told that the capacitor can only charge when the diode will be forward biased. So first I will find out the normal equation by applying KVL here. As you can see, the diode and resistors are both parallel to each other. So drop across the diode and the load resistance are equal. That is called V0. So if I apply KVL here, so if I apply KVL here, so what will get? Minus to plus, that is plus VI. Then voltage drop across capacitor plus to minus. I'll write down minus VC, then minus V0 equal to 0. So from this equation, our main objective is to find out the output voltage V0. So I got V0 equal to VI minus VC. So this is basically the output equation. So this is the output equation for the negative clamper. So this is the output equation of V0 equal to VI minus VC. So here, as you do not know what is the capacitor voltage, so and I told that the capacitor is only charged when the diode is forward biased. So you can see here, as the diode is connected like this, if I am providing a sinusoidal waveform, the positive half, due to the positive half, the diode will be forward biased and behaves as a short circuit, and the capacitor will charge. So when I am providing the a positive voltage, that means this end will be positive, this end will be negative, and the diode will be forward biased or acts as a short circuit. So after redrawing, you can see there, after redrawing, I am getting like this. The voltage VI I am connecting like this, so plus sign upwards, minus sign downwards, and voltage across capacitor is same as I have given here. Left hand side positive, right hand side negative. So I wrote here plus minus, and as this diode is forward biased and it acts as a short circuit, so all the currents will flow through this and resistance equal to 0. So the voltage drop of V0 equal to 0. So in this diagram or in this circuit, if I apply KVL, so I can get like this. So applying KVL, minus to plus, I will get plus VI, then plus to minus, I will get minus VC equal to 0. So I can find out your VC equal to VI. So capacitor voltage equal to VI. So as I told that the capacitor can charge up to the maximum voltage. So when this is a forward bias, the capacitor is charging up to the maximum voltage. As we have a maximum voltage as Vm, so the capacitor voltage I will get VC equal to plus Vm. Okay. So now this VC or the capacitor voltage what I got, I can apply here. So I can put here. So after putting this, so the output voltage I got, so the output voltage, so output voltage I got V0 equal to VI minus VC or V0 equal to VI minus Vm. V0 equal to VI minus Vm. Okay. So in this equation, this VI is the variable. So VI is a variable. So from different value of input voltage, I will get different output voltage. So let me write this. If I'll put Vi equal to 0, if I put Vi equal to 0, I will get V0 equal to minus Vm. Similarly, if we can put Vi equal to Vm, then I will get V0 equal to 0. Similarly, if I can put Vi equal to minus Vm, then I get V0 equal to minus 2 Vm. So these are some input output relationship of the input voltage and output voltage. So by taking this value, we can draw the input and output voltage waveforms. So let me draw the input and output voltage waveforms. So let this is your input voltage. We're having Vi. So this is the maximum voltage Vm. This is pi. This is 2 pi. This is the input voltage starting at the x-axis equal to 0. So now let me draw the output voltage. This is 0. Let I am marking this is minus Vm. I am marking this is minus 2 Vm. Okay. Now you can see from this relationship, when Vi equal to 0, at that time V0 equal to minus Vm. That means your waveform is starting from the minus Vm. Your waveform is starting from the minus Vm. And when Vi equal to Vm at this place, so your V0 equal to 0. So I will get a waveform like this. I will get a waveform like this. And when I put Vi equal to minus Vm, this portion, so I am getting V0 equal to minus 2 Vm like this. Okay, so I am getting a waveform like this. So this is your the waveform starting from minus Vm, going to 0, again coming back to minus Vm, then again the minimum value is minus 2 Vm, then going back to 0. Okay, so now if you can see carefully, so previously the input waveform is starting from 0. Now the output waveform is starting from minus Vm. That means the particular input waveform is shifted downwards. Shifted downwards. Okay. So in the main thing you can find out also, if I can find out here V peak to peak voltage. So Vm and minus Vm. So I'll get here 2 Vm. The peak to peak voltage is 2 Vm. Similarly, if in the output voltage, if I can find out V peak to peak, same thing 0 minus 2 Vm. So I'll get here 2 Vm. So both the waveforms are similar, but we can able to shift the waveform downwards. We can able to shift the waveform downwards or in the negative direction. That's why it is called a negative clamper. So basically I can shift the waveform downwards. That's why we called negative clamper. I hope you understood this one. If you have any doubt, you can ask in the comment section, or if you find that this particular numerical is uh, good, then you can share with your friends. Thank you for listening.